In the last video, we talked about the four main decisions you need to make before collecting data. Today, we're answering one core question. How can we tell whether something truly causes an effect rather than merely appearing alongside it? This is a story of two scientific methods, observing the world as it naturally unfolds versus intervening in it. Statistics is the logic that helps us decide what we can and cannot conclude. Science has two primary ways to test a hypothesis. In correlational research, we observe what naturally happens without directly interfering, and we look for patterns of co-occurrence. In experimental research, we deliberately manipulate one variable and measure what changes, and that direct manipulation is the key feature that makes causal claims possible. The observer's path gives us a natural view of the world. We measure variables at a single point in time without changing anything, which often yields high ecological validity because it reflects real life. Typical examples are measuring pollution and number of fish, linking lifestyle factors like smoking or diet to disease, or correlating work satisfaction with management style. Useful, but still only describing relationships, not mechanisms. Here is the observer's dilemma. We may see a link, but we cannot prove a cause. The Coca-Cola contraception example shows the constraint clearly. Researchers used questionnaires to look for correlations between contraceptive use, including Coke, and pregnancy rates because assigning people to an unproven contraceptive would be unethical. The price you pay is that co-occurrence alone gives no proof that one variable caused the other. The hidden culprit is the confounding variable, a third, unmeasured factor that influences both variables and creates a misleading correlation. If you observe that breast implants correlate with suicide, it is a flawed conclusion to claim implants cause suicide. A plausible confounder like low self-esteem could independently increase the likelihood of seeking implants and also increase suicidal thoughts, producing the correlation without a direct causal pathway. The power of the experiment is the philosophical shift. To infer causality, we must rule out alternative explanations. The core principle is to compare two controlled situations, one where the cause is present and one where it is absent, so that any systematic difference in outcomes is credibly attributed to the manipulated cause rather than to background noise or hidden factors. Observation, experiment, causality. In the motivation and learning example, we test whether teaching style causes differences in learning by defining the independent variable as the teaching method with three levels: positive reinforcement, punishment, and a control condition with no motivator. We define the dependent variable as statistical ability measured by an exam, and the crucial insight is that the control group provides the baseline where the cause is absent, so differences in scores can be attributed to the teaching method. There are two classic ways to structure an experiment. In a between subjects design, different participants are assigned to different conditions, like one group receiving praise, another punishment, and a third the normal seminar. In a within subjects repeated measures design, the same participants experience all conditions over time, which can reduce variability but introduces ordering issues that must be handled carefully. Statistics is fundamentally about separating signal from noise. The signal is systematic variation created by the experimental manipulation, like improved performance due to bananas as a reward, while the noise is unsystematic variation from random factors such as natural ability, time of day, mood, or measurement error. The practical goal is to estimate how much observed variation is truly systematic versus merely random fluctuation. Experimental design determines statistical power because power improves when the signal stands out against a quieter background of noise. In repeated measures designs, unsystematic variation is often lower because the same participants appear in each condition, so stable individual differences cancel out. In between groups designs, noise is often higher because different people bring different baseline levels, increasing variability and making real effects harder to detect. Randomization is the ultimate weapon against bias because it minimizes unsystematic variation and, crucially, helps eliminate other sources of systematic variation that could masquerade as your effect. By randomly assigning conditions, we make it likely that confounders are evenly distributed across groups, so systematic differences in outcomes can be attributed with more confidence to the manipulation rather than to some hidden factor. Randomization looks different depending on the design. In repeated measure studies, the problem is practice or boredom effects across time. So the solution is to randomize or counterbalance the order of conditions so no condition always benefits from coming first or second. In between group studies, the problem is that groups may differ on key characteristics before the study even starts. So the solution is random allocation of participants to conditions to balance those characteristics on average. The final verdict is that correlational research aims to identify relationships and see how variables co-occur in the world, but causality cannot be inferred because of confounding threats, even though the approach often has high ecological validity and can address questions where experiments are unethical. Experimental research aims to establish cause and effect by manipulating a cause and measuring its effect, offering high internal validity and stronger causal conclusions, with the core question shifting from are X and Y related to does X cause Y. The researcher's true task is to discover how much variation there is in performance and then determine how much of that variation is systematic and how much is unsystematic. The choice between observation and experimentation is not a mere technicality. It is a strategic decision that determines whether we can isolate a true causal signal from the random noise of the world. Thank you for watching this video. If you liked it, make sure to like and subscribe. See you at the next lesson.